Hi, welcome to AB Video 3.4b Part 1, the second derivative test for relative extrema. So here is the actual second derivative test. You have a function f, and it only works, the second derivative test, if you have a critical number that makes the first derivative equal to 0. So if any of your critical numbers make the first derivative undefined, you will not be allowed or able to use the second derivative test. And the second derivative of f has to exist on an open interval containing c. So there's two hypotheses. One, you have to have a critical number where the first derivative is 0, and your second derivative has to equal a number. It cannot equal infinity, negative infinity, or does not exist. So if that's true, and if the second derivative is positive, then f has a relative min at CF of c. If the second derivative is negative, it has a relative max. If the second derivative is 0, the test fails. That is, f may have a relative max, relative min, or neither. In these cases, you're going to use the first derivative test. So basically, this is what we have going on. Okay, if you have your second derivative is positive and your first derivative is 0, as you can see, we have a relative max. Min. So second derivative positive, first derivative 0, you'll notice we have a min. Whereas if the second derivative is negative, concave down, and the first derivative is positive at that location, first derivative is 0 at that location, then you have a max. Okay, so you have to have the first derivative equal to 0, and your second derivative has to either be positive or negative. If it's 0 or doesn't exist, you can't use it. And if your critical number does not make the first derivative equal to 0, you cannot use it. Okay, so again, it's for relative extrema, the second derivative test, not for points of inflection. So keep in mind that if your first derivative is 0 at this critical number, then it's a horizontal tangent line. If the second derivative is positive, that means your graph of f is concave up. And the second derivative is negative, it's a maximum. So the problem that people make the wrong association. They see positive, they think max. But you got to keep in mind that if the second derivative is positive, the graph is concave up, which means there's a min, not a max. So it's kind of opposite signs, if you wish. When the second derivative is positive, you'll have a min. When the second derivative is negative, you'll have a max. If the second derivative is 0 or doesn't exist, the test fails. You'll have to use the first derivative test, which, by the way, always works. Now, here's a common AP multiple choice question. They don't even mention the word second derivative test. However, it's telling you that the first derivative at 7 is 0, and the second derivative at 7 is 8, which means it's positive. Hence, you have a horizontal tangent line at 7, and the graph is concave up. That means you're going to have a relative min. Okay, so this is like number 42, and I'm going to show you both ways. I'll show you the right column first, which is the old-fashioned first derivative test. We'd find the domain, all real numbers, gets a polynomial. There's no vertical asymptotes. We'd find the derivative. It never doesn't exist. It equals 0. You factor, blah, blah, blah. So you get a critical number of 3. You find out that the first derivative is positive on both sides. Hence, there is no relative extrema at x equals 3. If you tried using the second derivative test, you'd start with the same thing, which is you'd start with the domain, vertical asymptotes, find out where the first derivative is 0. Now it is 0 at 3. So now you'll have to find the second derivative, which is 6x minus 18, plug in the number c that makes the first derivative 0 into that, and unfortunately here we get the second derivative is 0, so the second derivative test fails. So when you're comparing these two tests, here you have the extra added chore of finding the second derivative. Here you have the extra added chore of making a number line and checking on both sides. So this is actually faster, the second derivative test, if you can use it. Let me go back there and get that out of there. Okay, find the relative extrema using the second derivative test. I don't know why it says tests. So here they want you to use the second derivative test. So here's their original function. I figured an easy way to do this would to pull that square on the outside and to actually expand that. So now my domain is all real numbers, polynomial, there's no vertical asymptote. The first derivative is negative 2/8, which is 1/4, times x squared minus 2x minus 8 to the power of 1, times, by the chain rule, times the derivative of that. So I could pull out the 2 from here, and then the 2 over 4 will be a half. When I pull out the 2, that'll be x minus 1. And this factors into x plus 4 times x plus 2. So here it is all nice and factored. It never doesn't exist. And of course, what we're interested in is what are the critical numbers that make the first derivative 0? Well, it's 0 when x equals 1, or 4, or negative 2. So there's no number line. All you do at this point is figure out what is the second derivative at 1, at 4, and at negative 2. So I would have to find the second derivative of this function, which I really don't feel like doing very much, but here goes. I took it from this version, and you notice how I put these purple parentheses, so that's my first factor and that's my second factor. So it's first factor times derivative of second factor plus second factor times derivative of the first factor. You don't need to really simplify that, because now what you're going to be doing is replacing those x's by 1, by 4, and by negative 2, which are the three numbers, the three critical numbers that make the first derivative equal to 0. And when you plug those numbers into the second derivative, believe me, you'll get 9/4, negative 9, negative 9. So you can see that since the second derivative is positive, remember that's concave up, which means it'll have a relative min at 1 comma g of 1. Same thing for both of these. The second derivative is negative, so the graph is concave down, which means you'll have a max at 4 comma g of 4, which happens to be 0, and negative 2 comma g of negative 2, which happens. And that's the end of video 3.4b, part 1.